welcome back to the topic on atomic structure. We were studying the quantum numbers in the previous video. We have studied that one, and in continuation of that one, the quantum number called azimuthal quantum number explains the shapes of the orbitals. So we shall have the shapes of the orbitals. First, let us consider the shape of the s orbital or s subshell. This s orbital is having the spherical shape. Spherical shape. So we can consider this as a nucleus, and around that one there is a spherical space where the electron is revolving in the atom in the s orbital. So this orbital is named as the 1s orbital. That is the first shell containing the s orbital. This is the second spherical shape, that is named as the 2s orbital. So the shape of the s orbital is actually spherical. Coming to the p orbitals, these p orbitals are having the dumbbell shape. Dumbbell shape. So when we consider that magnetic quantum number, there are three orientations in the p orbital. So that m is equal to -1, 0 and +1, which indicate that there are three orientations for the p orbital. And when we consider this dumbbell shape of the p orbital, this we can resolve in the x, y and z axis directions. So when we consider this p orbital along the x axis, we write this as x axis. So we are having the dumbbell shape along the x axis. So this orbital is called as the px. Usually these two lobes are indicated with the positive and negative sign. Means whenever the electron passes from the positive lobe to the negative lobe, it passes through a point where the electron density becomes 0. This we will consider in the later part as the nodes. So there is one node, one place where the electron density is 0. Similarly, when we consider this as the y-axis, there are two lobes along the y-axis. So this is called as the py orbital. Again we write one lobe with positive sign, the other lobe with the negative sign. So similarly, when we consider this z-axis, there are two lobes, one with the positive and the other with the negative. So it is the pz orbital. Altogether when we write these three px, py and pz orbitals, we write this shape like this. So this is x-axis direction, this is y-axis direction, this is z-axis direction. These are the three mutual axes, perpendicular axes. So when we consider the lobes, along the x-axis we have this px orbital. When we consider this lobe along the y-axis, we have this py orbital. When we consider along the z-axis, it is called as the pz orbital. So this px, py and pz orbitals, they are actually perpendicular to one another. So this red indicates py orbital, this black px orbital, this is pz orbital. But as far as the energy of these three orbitals are concerned, px, py, p orbitals are concerned, they are all equal. And hence, such equal energy orbitals, they are named as the degenerate orbitals. Degenerate orbitals. When the energy of various orbitals are equal, then they are having the degeneracy, or such orbitals are named as the degenerate orbitals. Now let us consider these shapes of the d orbitals. As the magnetic quantum number indicates, there are 5 orientations. So these 5 orientations can be indicated with the shapes which are actually indicated as dxy, dyz, dxz and dx2, y2 and dz2. When we consider these three orbitals, these are present in between the axis, that is in the plane produced by the axis. So xy plane, yz plane and xz plane. And these two are present along the axis. So two lobes along the x-axis and two lobes along the y-axis, that is indicating dx2, y2, and two lobes along the z-axis indicating the dz2. So first let me write this first set, dxy, dyz, dxz. Suppose you consider this as xy plane, x-axis and y-axis. The plane produced by these is called as the xy plane. So this d orbital is having double dumbbell shape. Double dumbbell shape. So we can write two lobes along the x-axis and two lobes along the y-axis. This is dxy. Suppose you consider this y-axis and z-axis. Y-axis and z-axis. Again, when we write the lobes in between, this dxy, the plane produced by the x-axis and y-axis. These will contain two lobes, x and y. When we consider this y-axis and z-axis, we have these four planes produced by the y and z axis. So the lobes present in between are indicated as the dyz. This is dxz. Similarly, when we consider this x-axis and z-axis, the plane containing x and y axis are produced by the x and z axis. They will contain the two lobes each like this. Otherwise, so this is actually dxz plane or dxz orbital. Otherwise, you just go on changing the axis. If you consider this x and y axis, it is dxy. dxy. If you consider y and z, suppose you consider this as y and this as z, it becomes dyz. If you consider this as x and z, then it is dxz. So, double dumbbell present in the plane produced by the two axes is indicated as dxy, dyz, dxz, dx2, these three orbitals. Let us consider the shapes of the dx2, y2 and dz2 orbitals. Suppose you consider this as x-axis and y-axis perpendicular to one another. If two lobes are along the x-axis and two lobes along the y-axis, it is indicated as dx2, y2. Some people pronounce it as dx square minus y square, but it should be pronounced as dx2 minus y2. If you consider this z-axis, this is x, this is y. Two lobes are along the x-axis and along the z-axis with some circular shape in between where the density of the electron becomes 0. So this orbital is named as the dz2 orbital. Some people pronounce it as dz square. So these are the shapes of the orbitals. S orbital is having the spherical shape. P orbital is having dumbbell shape, that is along the x-axis it is px, along the y-axis it is py, along the z-axis it is pz. But d orbital, when we write all the three together, we write these x-axis, y-axis and z-axis containing the lobes. Therefore it is px, py and pz orbitals. D orbitals are having the 5 orientations. So dxy, dyz, dxz, which are indicated in between the axis, the plane produced by the axis. 2 lobes each because it is having the double dumbbell shape. Similarly here, dx2, y2 and dz2, 2 lobes along the x-axis, 2 lobes along the y-axis, it is dx2, y2, and dz2 where the 2 lobes are along the z-axis. But this actually is called as the nodal plane, where the electron density becomes 0. So that we shall consider in the next part. So I hope it is clear. But as far as the shape of the f orbital is concerned, it is very much complicated. So simply you write, the shapes of the f orbitals are very much complicated. So let us not worry about the structures of or shapes of the f orbitals. Now after these shapes of the orbitals, s orbital, p orbital, d orbital, etc., let us consider a node. Node. Node is the place or the space around the nucleus where electron density becomes 0. So there are two types of nodes. This is the space where electron density becomes 0. Electron density becomes 0. Or there is no electron density at all. There are two types of nodes. One is called as the angular node, which is also called as the planar node, or it is also named as the nodal plane. So this is actually a plane passing through the center of the nucleus where the electron density becomes 0. Now suppose you consider this s orbital. If you draw a plane passing through the center at any point, it will still contain certain electron density. Okay. That is, when we consider this as a nucleus and this as the s orbital, if you draw a plane like this, passing through the center, it contains electron density at this place. Similarly, you draw a plane passing through the center like this, still it contains electron density. That means, for the s orbital, there is no any planar node, and there is no plane where the electron density is 0. That means, for such angular node, it is calculated by using the value of L. For s orbital, L is equal to 0. So L is equal to 0. Therefore, number of angular nodes is 0. Angular node is equal to 0. If you consider p orbital, for this L is equal to 1. Therefore, angular node for the p orbital is equal to 1. Now let me consider this px orbital. This is along the x-axis. If you draw a plane passing through this center, it does not contain any electron density in the px orbital. For each of these px, py, pz orbitals, the angular node or planar node will be 1 each. Similarly, for the d orbital, L is equal to 2, therefore the number of angular nodes is equal to 2. So like that we can calculate. For the f orbital, L is equal to 3, therefore angular node is equal to 3. This is one type of node that is called as the angular node or planar node. The second one is the radial node. Radial node, it is also named as the spherical node. This is the spherical space around the nucleus where electron density becomes 0. For example, this radial node can be calculated by using the equation n minus L minus 1. Say for example, for the 1s orbital, n is equal to 1, s is, for L is equal to 0 for the s orbital. Therefore, we have this radial node is equal to 1 minus 0 minus 1, that is equal to 0. For the 2s orbital, this becomes 2 minus 0 minus 1, that is equal to 1. That is, if you write 1s orbital here and 2s orbital here, there is a space between these two where the electron density becomes 0. For 2s orbital it is 1. For 3s orbital it is 2. For the p orbital, we can calculate this one as n minus L minus 1 is equal to, for 2p orbital, it is 2 minus 1 minus 1, that is equal to 0. For 3p orbital, it is 3 minus L is equal to 1 minus 1, it is equal to 1. So like that we can calculate the radial nodes for the various orbitals. Therefore, by using these two, we can calculate the total number of nodes is equal to n minus L minus 1 plus L, that is equal to n minus 1, where n is the principal quantum number. For example, for 1s orbital, n is equal to 1, therefore total number of nodes is equal to 0. For the 2s orbital, it is 2 minus 1, that is equal to 1. For 2p orbital, again 2 minus 1, that is equal to 1. So like that we can calculate the various types of nodes. In the next video, we will consider how to write the electronic configuration by using the various quantum numbers. There are some rules to use to write the quantum numbers, to write the electronic configurations. Thank you.